So my talk today is an innovative double pulse technique using a pre-RF pulse and DC-IV measurements. So the outline of the presentation is the following. So I will introduce the context of the study and of this research. I will also talk about the compact modeling and typically for GaN transistor and the impact of traps and the time dedicated to traps model. I will do a short part on pulse IV measurement for trapping model, so standard pulse IV measurements, basic double pulse measurement, and also I detail the pre-RF pulse IV measurements for the talk today, the principles, the measurement setup, also the comparison between the different methods, and the procedure of this measurement. And by the end, I will talk about the advantages of this new approach. So, you know, it's a very iterative process to do a compact model. So we used IV and S parameter characteristics. In the first step, we use 0,0 characteristics because we suppose that the traps and thermal effects are negligible for this condition. And we will step by step extract a model. So we do an extraction to have the linear model. And after that, we do the nonlinear elements like nonlinear capacitances and the nonlinear output current. So that is a key part of the compact model. After that, we will perform some specific characterization in transient and in IV network in order to highlight and understand the traps effects and also for thermal effects. And we will implement in compact model. At the end of extraction, this compact model will be validated against load pull measurements and large signal performances because it's a very very important thing to do to help the designers after. So I put here that to compact model, we need to have very precise IV characteristics in different conditions in order to exhibit successively trapping effect and thermal effect. So we will do transient, IV characteristic from different Christian bias. And we will go after to the load pull validation. And you know, when we go to this comparison, sometimes we need to do some compact model refinement because some possibilities to that is that the IV characteristic used to extract the model, in fact, are not in agreement or are not comparable with the IV characteristic C during the load pull measurement. So this is due to the non-dynamic take into account the charge and the traps for the gate and for the drain. So this slide is just to show you how the trap model is implemented in compact model. So you can see the schematic. So you have a topology of a typical model, and you have a traps blocks in front of the output current nonlinear current source. In fact, this blocks is tuned and optimized in order to modify the gate command C by the nonlinear current source. So in order to develop the trap model, we will do some characterization, so transient characterization. Here we put one example. It's a drain lag characterization. Drain lag measurement, I think you know, but it's, in fact, we will fix the gate voltage, and we will fix this gate voltage to have a low output currents in order to didn't combine thermal effect and traps effect. And we will pulse the drain voltage to a Christian bias. So we can see inside the pulse, in fact, the capture process. and after the end of pulse, the emission process. So here it's an example of fitting curves by the trap model and compared to the measurement. After we have done this kind of extraction and optimization, we will use also IV characteristic from another accretion bias. So here the example is done for VP and certain VDS0 is in IB class typically. And you will shape and tune some parameter for reproduce the shape of this network. And we can do this job for different quiescent bias, so AB class, C class, it depends on the needs. So here it's an example with a standard pulse IV measurement. So Jean-Christophe before present some characteristic like this. So here the measurement are for two quiescent bias. So you can see a network for 0,0 quiescent bias in blue and another in black for VP and 25 volts. So you can see that the graphic is divided in two parts. The blue part is for VDS superior to the VDS 0 voltage. So you see that the two networks will be similar result. This is due that the fact, maybe I have a pointer, no. So it's due, if you look at right of the slide, you have a blue curve and a red curve. And if you look for the blue curve, you have always upward pulse. So the measurement is performed during the capture process. And now if I look the pulse on the red curve, in fact, so if I go to VDS superior to VDS 0, I am in the upward pulse also, so I measured during the capture. But now if I go back and I go on VDS inferior to the VDS 0 voltage, you see you have a downward pulse, in fact. And the measurement is performed during this emission. And if the emission time of the component of traps is very long compared to the measurement, in fact, we measured at the beginning of the emission process. So the traps effect in this case are only excite, and the charged state is only due to the quiescent bias. So this is a limitation, in fact, of the high-V characteristic in classical pulse mode, because we don't take into account the variation, the dynamic variation of traps. That's why some research, and we can find some in literature some study on that. A basic double pulse measurement have been introduced in order to fix the traps effect. So here in this slide we have a certain chronogram. So you have different steps. Step 1 is for the quiescent level. So you can see the red point on the IV network that corresponds to this quiescent level. After step 2, it's the beginning of the pre-DC pulse to fix the traps. And we go to point A. At point A, it's at the end of the IV network. So why is this configuration? It's because you go to an important VDS value and a very negative VG pulse in order to have a trap, to maximize the traps effect. And when you fix now, you can go back to the quiescent value. So it's step 4. The time of step 4 can be moved and can be varied. And we go to point B, that is the pulse for IV measurement now. So in fact, in this configuration, the charged trap state is fixed, in fact, by the pre-DC pulse of the measurement. But we see that, and is the subject of this innovative measurement, we see that during using this basic double pulse measurement, we have a charge state fixed, but in a real excitation signal with RF signal, this is not exactly the same excitation of traps. So here it's another example for basic double pulse techniques. So you can see here a chronogram, and you have a comparison between two networks for two different quiescent bias, so 1 and 2. And you see that for a standard pulse IV measurement with just one level of pulse, you see that from the different network, we have a difference between blue and red curve. Now, if we use a double pulse technique, you see that from the two accretion bias, you have a similar network. When you see the large signal performances, so you have an example here of the average output current in function of the input RF source. And you see here the red curve is the measurement. And you see typically characteristic with a hole during the sweep of the input power. You see this hole is a signature of traps, in fact, during the measurement. And in blue, it's an ideal simulation of a compact model without any traps model. So we see that without traps model, we are not able to reproduce this kind of characteristics. Now we put 4 points in this characteristic to see the load cycle, so the charge cycle, on the IV network. So here you see that for the two first points in green and purple, you have a very a little variation of the charge cycle in the IV network. So we have no very big impact on traps and on charge states. So now if I go to an input power around 10 dBm, you see in the whole of the characteristic, you have now an envelope of the RF signal that is more, and that will be excite and modify the trap states and cause this kind of characteristics. After we go in the saturation area, so in the saturation area you have generation of some harmonics, and this is why the current increase again. So in that case, the RF signal envelope, in fact amplitude, induce variable trapping effects. And if you perform only a basic double pulse characterization and you do some output current nonlinear current source, you don't take into account this real excitation of traps during large signal characterization. So that's why we have would like to combine, in fact, the pulse IV characteristic, so classic pulse IV characteristic with one pulse on the gate, one pulse on the drain, and with a VNA-based load pool. So we have here an RF pulse source from VNA or external RF source. And with the bias T, we combine both the pulse IV, DC IV, and the RF pulse source. And we have also tuners at the load side to modify, in fact, the impedance. Why? It's because, in fact, the load cycle will be changed in function of your load impedance. And we have no the same trap state in function of the load impedance. The aim is to, on the IV network, to divide this IV network in different areas. So here you have the red, the blue, and the green area. And these 3 areas are centered around a certain crescent bias point. And here you have a low level for the green area. You have a low level of RF input signals. So you will pulse the RF signals, and after this pulse, we will perform a standard pulse IV measurements. So in fact, the traps are now fixed by the envelope of the RF signals, and after we will measure the IV points to reproduce your IV network. And the aim is to, from load pool measurements, to see the variation of V1 and V2 comment in function of the input level, and determine what are the level of my RF source I put and what are the DC levels after. So I will explain in other slide my sentence. So here just I will increase, I will go to the RF source with intermediate level and high level to describe, in fact, all the evolution, and my entire IV network. So based on all this theory, we have performed some comparison between the different methods. So in red, it's a network on, so it's a GAN HEMT, and you see the size here, and we perform classic pulse IV measurement. So you have the red network. And we have compared that with a standard, the basic double pulse measurement, and with the HAMCAT double pulse technique. So we can see that for, maybe, I have some animation. So at low RF power level, we have a trapping effect, in fact, induced by the low RF signal. So here, the signal is very low, so it doesn't affect the traps. So it's just due to the quiescent bias. And in this configuration, you see that with classical pulse IV measurement and with HAMCAT double pulse, we have a similar result. But in the case of basic double pulse technique, in fact, we overestimate the traps effect in this configuration. So after, if I increase my RF signal, you see that for higher VGS, I have an underestimation of the traps effect when I use pulse IV measurement with a standard pulse IV. And nevertheless, the basic double pulse technique and the HAMCAT double pulse give the same result. So in the case of a very large RF signal, in fact, basic double pulse and our method gives the same result. But the double pulse in low VGS didn't give in fact, it overestimates the traps. So it's not a real trap state that in the large signal performances. So HAMCAT double pulse techniques allow pulse IV measurement with a dynamic trapping effect induced by the RF signals. So the measurement procedure for this new approach. So in fact, we define the bias point, so the quiescent bias point for the application. After, we will perform some time domain measurements, drain lag, gate lag, to define what are the timing for the pre-RF pulse, what are the timing for the DC pulse, and what are the delay between these two pulses. The aim is to be sure that for all IV points, we go back to an established state and not go in emission time or capture time. So just to be sure, we go back to established state. And after that, we will do preliminary large signal measurements. So we will bias the components with a classical condition with pulse on gate and pulse on drain, and we will perform some load pool characterization, and we move the load impedance. With this measurement, we will determine the MXC and MXP, for example, or maximum amplitude. And from this measurement, we will collect the power wave E1, B1, A2, B2. And from this power wave, we can calculate V1 and V2 in function of the input power level. And we have a low variation of this V1 and V2. And we can, in fact, with this law, we can do a setup with a variation of V1 and V2 in function of the input RF level. And after, we will do a sequence, so the sequence with the right width for pre-RF pulse, right width for DC pulse, and period, etc. of the signals. And we will perform the measurement on the component with this sequence. So here it's some results on GAN on SIC. And you can see, so the blue network is with IV standard characteristics, with simple pulse. And the two other are from the new approach, the double pulse. So you see, you have two results, in fact, in function of the load impedance presented to the component. You see the network measured at MXC and the network measured for MXP. So you see that for all the network, you have the network in red at MXC that presents current lower than for MXP. The hypothesis for that is that because the VDS swings for MXC is higher than for MXP. So we think that the traps, in fact, are maximized in this configuration. That's why, due to the trap state, the current is lower than for MXC. And the aim with this network is now to go to compact model and use this new kind of characterization to directly extract some output current parameters, and no use of, it's not necessary now to implement trap blocks, in fact. We would like to have directly an output current source with the effect of traps, without added some traps block after. And we go directly to the load pool validation. And on this load pool validation, due to the fact that the network and the output current source will be optimized in the real excitation of traps, we have a comparison between load pool measurement and now with the model is directly good. So we have in this model flow, we have do some histogram to represent the time spent in whole step of the characterization and extraction of model. So at the beginning, for pulse IV measurement and load pool measurement, in fact, is compensate because in the standard compact model flow, we will use more IV characteristic and more S parameter measurements. But in the using AMCAT double pulse technique, we will do more load pool characterization. So in terms of measurement time, it's similar. But the aim is at the end, in fact, of the modeling process. So all the process is the same without traps block now in this. Okay. In traps block. So now we have a model validation refinement is directly good, in fact, because we are sure that we are an output current source that is in real case of application. So the reduction time, in fact, is around, it's an estimation for the moment, and it's around 30%. So to conclude on my talk, in fact, we see that extracting with this new technique, we can extract some compact model in realistic operating condition. It's just with an optimization of the nonlinear current source, it didn't necessary to add some traps model, in fact, to have a good correspondence in load pool performances. We used a classical VNR-based bench, in fact, to perform this new characterization. And with the help and thanks to this new approach, we spend no more time in a refinement and model. And this is reduce the back and forth optimization process. So thank you for your attention.
Thank you.
Hello.
Hello.
So I just wanted to know when you do measurements using AMCAT system, only IVCAD, and
yes.
Do you do all the measurements within the same measurement window, or you use different measurement windows for IV, then S parameters, then load pool?
So when you perform when we perform IV and S parameter, in fact, yes, you have a measurement window, so it is the same. In that case, the measurement window will be in the DC pulse. So you have a RF pulse before, no window, and the measurement is realized in the DC window, in the DC pulse.
So basically, when you if you want to avoid heating effects when you do pulse IV measurements,
yeah.
So you can go in IVCAD, as far as no, you can go lower to, I think, 400 nanosecond or something in measurement window. But if you do S parameters, you can go minimum to 1 microsecond, as far as I remember.
Yes.
So
Typically, we are
so there will be difference in self-heating effects and how you make sure that you extract a model using same thermal constants.
Okay, so yes. For certain components, in fact, yes, if you use a width of 1 microsecond, we can see on the characteristics, at the end of characteristic, for high VDS, you can see a decrease of your output current. The aim in our case is to extract model. So firstly, we do the characterization for 0, 0, and we consider that at the end, the line is straight, okay? And after, we will add thermal effects. So the aim is based on characterization to determine thermal resistance and capacitance. We will add after, and we will check that DC characteristics, long pulse measurement, and also the IV network from the model goes to the measurement. Okay. But in measurement, I understand when you perform measurement is 1 microsecond, we have some thermal effects. Yeah, I noticed that on certain components. The aim is to reduce, in fact, the width, but sometimes it's not sufficient. If you reduce too much the width, you have some big capacitance at the input of the component, and we didn't have time to go to an established state during your pulse, and it's necessary to increase. So I know at the end for high VDS you have some thermal effects.
Long live India and France friendship.